Okay, welcome back here. We're going to talk now about another quick chemistry topic and just kind of briefly highlight density is up on tap today. So, density is really this formula here. Density is mass divided by volume. Density of the object determines, for example, whether or not something will sink or float in water. If something is more dense than water, it will sink. If something is less dense than water, it will float. When we talk about the density of water, typically speaking, it does change with temperature, but most of the time people consider the density of water 1 gram per milliliter or 1 gram per cubic centimeter. And that is because 1 milliliter is equal to 1 cubic centimeter. A reminder that they are a 1-to-1 conversion between them. And those are the typical units that we see associated with density: mass up on top, divided by volume on the bottom. And that gives us units of grams per mass and milliliters per volume. So grams per milliliter is a very typical unit we associate with density. Our grams per cubic centimeter, which is also very typical. And I would say these are the common units that you find for density for things that are in the solid state or liquid. So those are the very common sort of units that we find for solid or liquid. When you get to gases, and depending on what chemistry class you're in, grams per liter are typically the common units that we find for gases. But I would say probably most of the time these are going to be your two really sort of basic units for density. So you should think of density, which is D is equal to M divided by V, as a formula that you can rearrange and really solve for anything that's present. So if we wanted to solve for volume, the volume would be the mass divided by density. There we're multiplying the volume to each side, and then we're dividing the density to each side, and gets us to our volume is equal to mass over density. We can also solve for mass. Mass would equal volume times density. And we get that the same way from our original equation. Kind of the first step we did there, we're just going to multiply the volume to each side. Those will cancel, and that will leave us there. So these sort of three versions of the density equation you will need to do and usually use a lot, because we do solve for any of them. Sometimes people remember this by sometimes commonly referred to as the DMV triangle. You go DMV, everybody likes to go to DMV, and you do a little density is mass divided by volume, mass is density times volume, and volume is mass divided by density. So you could kind of do the little DMV triangle there, and it'll kind of get you what you need if you like. So in this case, let's take a look at a couple of these sort of parts to density and sort of how we would get there. So for example, since density is mass divided by volume, how do we get the mass? Typically we weigh it out, and typically they are in grams. They may not always be in grams. You might have to convert it to some other unit, but you can't convert it to grams. Now, what about volume? There's kind of like three ways that we could kind of get a volume when we're dealing with density. One way is pretty simple. You just put it into some type of glassware. You take a proper reading of the volume that's in that glassware, taking a proper measurement. So again, I'll put a little link up here that you can look at the measurements video that we talked about earlier in one of these quick video lectures. So you could just take an actual reading of it. It's a very common way you can get the volume. Another common way is if you had some type of cube, you could take 3 length measurements, length times width times height, and that will equal the volume. Remember, if you have centimeters times centimeters times centimeters, So if you had a cube and you took like a ruler and measured in 3 directions, and you multiply them together, that gives you our cubic centimeters, which is a volume, remember. So again, as I said on the previous slide there, 1 milliliter is the same as a cubic centimeter. Essentially, if you cube any 3 sort of length measurements, you typically will end up with a volume. So those are 2 very common ways. So if you have some type of solid block or something like that and you want to get the volume of it, that's what you would do. If you had a liquid, you could put it into a graduated cylinder, and that is how you could get the volume of it. The third way that you get the volume of an object is actually volume by displacement. So we could do volume by displacement. And volume by displacement is a pretty simple idea here. We basically take a container and fill it with a liquid like water, and we have an initial sort of volume reading. So we would take a measurement of the initial volume reading here. We would take our object, some type of solid object, just typically works well with this. And basically what we would do is we would take that solid object and put it into the container that has the liquid. Now, when we put that solid object into that container, drop it in there. There we go. What's going to happen to the volume level is it's going to cause basically the volume level to rise to a final volume level there. And it's basically doing what the title is. It is basically displacing the water. So a solid object will displace a volume of liquid or like water equal to its own volume. So it basically will displace that same amount of volume. So to find the actual volume of the object that we put in there, it is basically the difference between the final volume and the initial volume. So the volume of the object can be found by displacement, final volume minus initial volume. And that is a very, very common way in density type problems that we can figure out the density of a solid object. So let's take a look at a couple of problems. It's a straightforward problem. Let's say we have the mass of a metal was 32.565. And it had a volume of 25.3 milliliters. So in this case, when we have a formula in chemistry, D is equal to M over V, obviously we're using density and we want to know what is the density in this case. That would probably be good to know what we're trying to find. So we're looking for what is the density in this case. We want to take out what we have. So obviously here we have a mass given to us. So we have that. We have a volume given to us. So there's that. So we could just basically put it in here. Our density would be 32.565 grams divided by 25.3 milliliters. Again, punching that into our calculator here, 32.565 divided by 25.3. That's going to give us a density of 1.28715,415. Again here, that's what it's going to look like on your calculator. And we want to figure out where we should end up. So we are dividing here. So we are going to look at significant figures. Top number has 5 sig figs. Bottom number has 3 sig figs. That means when we look at our calculator, we actually want to end up right there. That is 3 significant figures. Here we will need to round because of the 7, and we're going to round up, and that will give us 1.29. The units here do not cancel out, so grams per milliliter. The number stays with the top unit, which is grams in this case, and is per 1 milliliter in this particular case, and that would be the density of that object. Okay, everybody, let's take a look here at another example. So we have a solid with a mass of 52.365 grams, was placed in a graduated cylinder that has 16.4 milliliters of water. The water rose to 54.3 milliliters when the solid was put in there. what is the density of the solid in grams per milliliter? So let's take a look and see what we got going on here in terms of this problem. So if we kind of sketch what we got going on in this problem, we got a graduated cylinder here, award-winningly drawn, and it has a volume of 16.4 milliliters to begin with. That is our initial volume. We also have a solid here, also known as a square. 52.365 grams is that guy. So 52.365 grams. And we're going to put this guy into the graduated cylinder. So we're going to take this guy and put it in there. I know perhaps it doesn't look like it's going to fit, but we'll just imagine it somehow gets in there. And once we put it in there, we will see the level there rise to 54.3 milliliters in this case. And that would be our final volume. We obviously have our mass of our solid. And in this particular case, we're looking for the density here in grams per milliliters. So the density is again our mass over volume. We obviously have our mass giving to us. We do need to find the volume, and this is volume by displacement because again, as soon as that solid goes in there, it's going to displace that liquid equal to a volume of itself. So if we take where we started, just kind of draw a line-ish, and we take where we ended after the solid went in there, remember that the difference there is the volume of our object in this case. So the volume of our object will equal the final volume minus the initial volume. And in this example here, we have 54.3 milliliters minus 16.4 milliliters. And we will end up with a volume of, if I can find my calculator here, 54.3 minus 16.4, 37.9 milliliters in this particular case. So now we do have the bottom of what we need. We could put it in there. Density will equal our mass, which was 52.365 grams, divided by our volume of 37.9 milliliters. Gonna punch that in there, 52.365 divided by a 37.9. Hopefully I hit all the right numbers. Gonna go with, on our calculator, 1.381662269 grams per milliliter. Now, clearly, obviously, you don't usually keep all the numbers that you see on your calculator, and we are not going to either, but just to kind of show you the number that you will see on your calculator, that is what you get. Remember that the grams do stay, the number stays with the grams, and it's 1 milliliter. We do need to think about significant figures. So how did we get to our significant figures? So we want to remember our rules. The really first calculation we did was way back here. We were subtracting, which means we should be looking at decimal places. And this guy here has 1 decimal place. This guy here has 1 decimal place. That is why we took our volume to 1 decimal place. Remember that it has 1 decimal place, but in terms of significant figures, with that 1 decimal place, it actually has 3 significant figures. This is what I was talking about earlier. That's important to keep track of all this, because although we are going to decimal places in the case of the volume, ultimately now we're going to take that number and look at the significant figures. And we're going to do that because the last calculation that we did was dividing, where we do look at significant figures. So our mass number up on top has 5 significant figures. Our volume correctly done here to the decimal places ends up actually with 3 significant figures, even though it has 1 decimal place. And now our answer should actually end up at 3 significant figures. That's going to take us right there. And that means we should call this 1.38 grams per milliliter. Once again, the units do not cancel. The number stays with the grams, and it's 1 milliliter. So again, in this case, the answer significant figures is actually based off of the calculation you did here, where you went to decimal places, giving us 1 decimal place in the answer, but importantly as well, 3 significant figures, for the last calculation that we did over here. So again, you want to keep track of these significant figures in your calculations so that you do end up with the right answer when it's all said and done. All right, let's take a look at one last one here to finish up this video. If a solution has a density of 1.75 grams per milliliter, how many grams of the solution will be contained in 15.5 milliliters? So in this case, if we think about density here, which is mass over volume, we definitely have the density given to us. We also have the volume given to us. So again, it would make sense that we want to solve for mass. Remember, if you're not sure, you can do the DMV triangle. And in this case, mass would be density times volume in this case. So mass is equal to volume times the density. We're basically, again, multiplying the volume to each side. They're going to cancel and give us volume times the density. In this case, though, a lot of times we want to maybe show our work with dimensional analysis. And as we'll talk about, or maybe you've talked about, dimensional analysis is where we kind of use conversion factors and show the units canceling. So for example, the density value that we have of 1.75 grams per milliliter can be used as a conversion factor. You could use it as 1.75 grams over a milliliter, or a milliliter up on top and 1.75 grams on the bottom. Basically, conversion factors are just fractions. They could go one way, and then you could kind of inverse them or flip them around and put it in the other direction. So why would we want to do that? Well, when we have our volume here of 15.5 milliliters, we could set this up using dimensional analysis to see the units canceling. And how that works is like this. We would start with our 15.5 milliliters. We would use our density as a conversion factor. So how does that work? It's basically opposites, and opposite locations will cancel out the opposite or the same unit, basically. So if you have, say, in this case, although it's not written as a fraction, milliliters are up on top. So to cancel them, you basically need milliliters in the opposite location, which is on the bottom. And we would use it like so, 1.75 grams per milliliter in this case. Now, obviously, if we had grams and wanted milliliters, we would go opposite in this case. So you use whichever conversion factor where the units are opposite of each other so that they cancel out. How does that work? Well, a very simple sort of explanation of that is if I have 2 on top and I have 2 on the bottom, that equals 1. They essentially cancel each other out. So if I have milliliters, like in our example, up on top, and I have milliliters on the bottom, we just look at the units. We basically have milliliters times grams up on top divided by milliliters on the bottom. They cancel, basically equals 1. And that leaves us just grams. Now, when we do set it up in dimensional analysis like this, we have, say, unit A that we're trying to get rid of. We use a conversion factor that has unit A in the opposite location and, say, unit B, which is the one we're looking for. Now, when we set up something like this, anything that's on top gets multiplied. Anything that's on the bottom, you come back and you divide. So when you set it up in dimensional analysis, you're essentially only doing multiplying and dividing, which means you are going to be looking at significant figures when you're trying to figure out your answer. Now, if you had multiple conversions in a row, you could just continue down the path. Maybe you want to get rid of unit B. So got to go on the bottom and get you to unit C. In this case, unit A on top will cancel out with unit A on the bottom. Unit B on top will cancel out with unit B on the bottom. And the only thing left here is unit C in terms of this. Again, we would just keep multiplying as many things on top as you like. And then you'll come back and divide by everybody that's on the bottom. I will just give you a quick hint here. Maybe we'll have a future video on dimensional analysis. But essentially, this is the way usually in chemistry we like to show our work. And if you have multiple conversion factors that you're using, like I have here on the bottom, it's a really good idea. Once you get to the top and you multiplied everything, hit the equal sign on your calculator, divide by the first guy on the bottom, and then hit the equal sign. Divide by the second guy on the bottom, and then hit the equal sign. So sometimes people get the wrong answer when they have multiple things on the bottom that they're trying to multiply together because they try to put in their calculator incorrectly. So if you kind of follow that pattern, you can multiply as many numbers you want up on top, and then just hit equals when you're done. Come back and divide by each number individually and hit equals in between. You'll usually get always the right answer. All right, so kind of a quick diversion into dimensional analysis. We'll maybe have another quick video on that coming up, but let's come back to our problem here. Again, we set it up with dimensional analysis. Again, we're going to take our volume, and anything on top is going to be multiplied. Then we're going to come back and divide by what is on the bottom here. So in this case, we're going to multiply 15.5 times 1.75. And really, in this case, you don't need to really divide by the bottom because pretty much everything is a 1. You can divide by 1, but nothing's going to change. That's going to give us on our calculator here 27.125. Again, the units of milliliters on top and bottom will cancel. Leaves us only one unit up on top, which is grams in this case. Much like everything in chemistry, we still need to look at significant figures in this case. And when we look at our original number here for volume, that has 3 significant figures. When we look at our density value, the grams part there has 3 significant figures. That looks like A3 is a winner there. That takes us right there to the 1. And really, we should end up with 27.1 grams. So there's a couple of quick examples here to finish out this video on density calculations. Again, hopefully it's helpful. If you want any other topics, please let me know down in the comments. Otherwise, again, we'll see you on the next one. Have a good one. Bye-bye.